that he in 1930 thought that that a country like India requires an academy. And we have now 3 academies in India. And NASI has a large number of local chapters, about 22 or 23, and one of them a very active Delhi chapter. And people like Anirban, Papia, and many others. Professor Anurag Sharma is the chairperson of that. So we organize all seminars, which is supported by that. I wish someday we will start this offline seminar in which the students will get in touch with the speakers. And Sohini, I hope someday we will be able to hear you in person. I have heard a lot about you. So I thought I will just briefly mention about NASI. And it does a lot of work in many different areas. It has also good journals that it publishes. We encourage all the younger generation to think of publishing 1 or 2 papers there. With these words, I request you to give your talk. It is good to see you.
Before you start, I just want to add that Professor Ghatak is now President of the National Academy of Sciences, India. Yeah. So, Shoni, please continue.
Thank you so much. Thank you to the organizers. Hello, everybody. Namaskar, namaste. I'm very happy to kind of be there. I wish I could be there in person, but at least we can be connected this way. I'm particularly wishing that I was in India today because I'm looking outside and it's snowing here in Canada. So yeah, it would be much better if we could have had this in person. But still, I'm really happy to talk to you about this topic of mine, my own research field, which is quantum physics. But because this lecture series is special because it's focusing and celebrating on gender and women in science. So I hope you will bear with me because I also want to tell you a little bit about what that actually means to be a woman in science and what not just my journey in science, but my journey as a woman in this field and building a career. So with that, let me try, the hardest part of any talk is actually to make the screen sharing work. So let me try to do that first and see if that works. Actually, that didn't work.
It worked.
The problem is, I think I have to first put it into the other view before it worked, because last time then it didn't switch.
So just do whatever you have done previously.
Yes, exactly. So I'm trying to replicate the order.
And now it's full screen. Perfect.
Okay, great. So I hope you can see this.
Yes,
great. Perfect. So I guess, this is a very particularly special and challenging time thanks to the pandemic. And one of the things that I think we've all learned most importantly in this pandemic is the importance of healthcare, of course. I hope you can see my slides changing also. Is that?
Yes, it is changing.
Okay, great. You never know with these things. So yes, healthcare has been, as we know, a big issue. And the reason I want to bring this up is because I think it's a very important and relevant way, I hope, to introduce this topic I want to talk about, which is quantum computing. Because potentially in the future, this field will have more of an impact in areas such as healthcare, communication, and so on, which I hope to tell you more about. But particularly, one of the big challenges, as you know, is to be able to develop different kinds of drugs and medication, even vaccines, and generally being able to understand the properties of these different kinds of, essentially the chemical properties, as well as, the biological effects of things like, in the old days, we started learning about the structures of molecules such as penicillin. And that was sort of, the first steps towards this whole field of quantum chemistry and, understanding things at the level of individual molecules, and even deeper going at the atomic level and looking at electron structure and so on. And actually all of that is possible because of quantum theory, which is really the description of how matter and energy and individual particles interact with each other. It's a very strange theory, for sure. Turns out that that level, that scale of the universe is very different from our human scale. I'll try to tell you a little bit about that. But the reason I want to talk about quantum computing is because some of those kinds of calculations are still some of the hardest calculations we can do. So if we put all of the supercomputers of the world together and connected everything, and tried to use that kind of computing power, we would still not be able to really deeply calculate all of the properties of a molecule that is, let's say, has 200 atoms, which is not that big. And still, even that is already at the limits of our computing power. So going forward, imagine if we could have the possibility of doing those kinds of calculations really quickly and efficiently. It might change our abilities for all kinds of different applications, such as, of course, healthcare and drug development, but even things like materials design. Maybe we can build better solar cells. Maybe we can change, the climate issues that we're having, energy crisis, for the better. So there are many possibilities. Now, when I was a kid growing up, of course, I didn't know anything about quantum computing. But I loved science and I loved mysteries and I loved, all these science fiction TV shows like Star Trek. So I chose to go into physics, and actually initially I wanted to do mathematics. And then I realized that with physics, I can use mathematics, but I could study the universe. So that's what I chose to do. But very quickly, I found that my classrooms were kind of not the most comfortable for me, because often I was the only woman in my physics classes, and it was quite lonely. And over time, I started thinking about this also as a research problem, as in, why is it that women are so underrepresented in certain areas, physics, computer science, some areas of engineering? And also, is it actually true? Are there really no physicists out there who are women, or who, why is it that there's only one particular type? And you can actually do this kind of research yourself and try to find out more about what does the field of physics look like. And in general, if you want, you can try to figure out what does a science community look like? For example, these days, the easiest thing you can do is go on Google and try to do a search. So that's what I did, just as a quick test for you to see. So if you go on Google, you can click on the search and type in famous physicists. And if you type famous physicists, you will see some set of results. And these days, Google gives you a lot of nice pictures. So here's what you get when you do the search. So when I did the search, this is what I find. I have a whole series of images, and you can see that, of course, they're all men. And in fact, this is not the only results. You can scroll through all the different results that you get. And I hope you can see again these images, and you can do the search, of course, yourself. And you scroll through and you see some more images. You will notice that at least Chandrasekhar is on the results. But again, you see that there's very homogeneous list of all these men who Google has picked out as famous physicists. And you can scroll some more and scroll some more and keep going, and you will see that there's really no women. Google also thinks that women are not part of physics today. So of course, Google has learned this from our own sort of algorithms. And in Canada, for example, I can tell you that there was this recent poll in 2019. Now, 2018 was a very special year because in Canada, everybody was celebrating because Donna Strickland became the third woman to ever win a Nobel Prize in physics. And she's Canadian, and she's actually next door, my neighbor in Waterloo. So it was a very exciting time, and we were all celebrating. But then this poll came out, which showed that half of all Canadians can't name a woman scientist at all of any area. Forget about the Nobel winner. So that's kind of depressing. No wonder Google doesn't know that there can be women physicists. There doesn't seem to be any. However, I would suggest you do another search as well on Google. Instead of doing famous physicists, put in famous women physicists. And then you will see there are many, many results. I won't show you all of them. I'd like you to go ahead and do that yourself, and you'll see how many there are. So it's not true that there are not women who've done physics. From the beginning of time, women have been part of this field. But often we have deleted and erased them. So what's going on? Why is it that we don't know about women in physics? And what is it that made my classrooms, and probably even today, classrooms don't have equal numbers of students, boys and girls, who want to study physics. In fact, I believe it's something like 1 in 5 is a woman. So what's going on? Well, one of the things that I'm sure many of you have heard, if you have thought about this problem, one thing that comes up a lot is that physics is a very hard topic, and you have to know lots of mathematics, and so only very smart boys can do mathematics and girls can't do mathematics. So I want to explore that just like a research question. As scientists, we should be looking at data. So here's some data for you to look at. This is what's called a standardized PISA test, which is I can't remember what the acronym is, but it's basically a science test which is given to students across the world. It's the same test. These are all the OECD countries, and these are, I think, grade class 7, 8 kind of level students, and they're just assessing what is the performance of boys versus girls. And what you see here is that the bars, the marks where the bars are below the horizontal are where the girls are doing better, and when the bars are above the horizontal line, the boys are doing better. And what's important here to see is that there's not a standard, meaning it's not that the bar is always above the line. In some countries, girls do better, and in some countries, boys do better. So there's not some standard results showing that, yes, girls don't do well in science and math, girls just can't be better than boys, and boys are always better. That's the key message here, that obviously what's happening here is that what the classroom looks like or what's being taught matters, what the environment is matters, which country you are matters. So it's not the case that there is some significant deep biological difference in that is the reason for boys versus girls in science. So there must be something else there. And I can show you also data for India itself. So there are also standardized tests in India, for example. This is from a few years ago, but I think there are more current data sets as well. This one shows, for example, mathematics performance in class 8. And again, you see that in the blue areas, boys do better, and the orange areas, girls do better. And then there's a lot of yellow where there's not really a difference. And again, it's not that the whole map is blue. In fact, the majority of the map here you see is more orange and yellow than blue. And the same is true if you look at science, that there's certainly more blue here, but there's still orange, there's still yellow. And the point is that there's not a significant, it's not that everything is blue. So often we think of the wrong problem when we look at these kinds of issues in society, and we address things like, well, let's make some more mathematics camps, or try to teach the science to girls more, and so on, to try to bring them into the field. But it's not about performance. So we should really not be thinking about it in those terms when we try to understand what's happening with women in science. So then if it's not about the math, then why is it that the classrooms are not equally divided? Because everybody seems to be equally more or less good at science or not good at science. So what is going on? As I said, for me, it was very useful to think of this as a scientific problem. So there's also more data and more studies which does show what the real problem is. So for example, here was a very interesting study done where the researchers were monitoring parents and their children in a museum, a science museum. And they were just watching how parents were explaining science to their children when they asked questions. And what they found is that both fathers and mothers spend a lot more time and effort explaining science to their sons compared to their daughters. And it's not because the parents were very bad, they were very well-meaning, but unconsciously, they didn't even know that they were doing this. So there are many such kinds of unconscious biases and behavior patterns we have, where we assign certain roles to, men, women, boys, girls, and so on. And these are, of course, play a very large role. Of course, parents are very important when a kid is growing up. I was lucky because my parents were very supportive of everything that I did. And we had books and games, and I played with Lego, and I played with dolls and everything. But those kinds of influences are very, very important. So impact of parents, impact of teachers, these things are absolutely important. So it's not about whether or not the skills are there, but it's about whether there is this supporting environment and building that sense of belonging in science. Here's another test, which is kind of a lot of fun, which is a very simple one. It's called the Draw a Scientist test. And so students are asked from a young age to start drawing scientists, and as a test to see what they draw. And I think you can guess that if you ask, let's say, you're somebody, a young person to draw a scientist, what would they draw? So there are thousands of these drawings out there. This has been a long-term running experiment. One of my favorites I can show you is this rather crazy looking image, but it's also quite typical because these drawings are some representation of Einstein. And in this one, you can see that the student has very clearly written E equals mc squared, just so you know who they are thinking of. But the rest of it is a little bit worrying. But here's what's really interesting. This is quite universal. Everybody draws mostly Einstein, but certainly the majority draw men. However, there was another follow-up experiment done where in one classroom, they invited a woman to come and speak, kind of like in this Women in Science lecture series. And she deliberately didn't dress like a scientist. She wore this very colorful costume, and she talked about her science. She never talked about being a woman or anything about gender. She just talked about all the science that she's doing. And then many months later, they did the Draw a Scientist test again in that same classroom. And this is what the students draw. So it's not that hard to change how we think about who is a scientist and how we can think of ourselves doing science as well. So that's the good news here, that maybe we don't have as many women in the classroom as we should, but that can change over time. And imagine how much we can broaden the talent. And finally, I want to say that there are other pieces. It's not just in the classroom. Building a career requires many things. So you need to have funding and resources. You need to have support at home. As we know, women still all over the world, certainly in India, in Canada, whether you're in a developing country or a developed country, turns out that women still do the majority of the housework and the childcare. And that absolutely is something that needs to be taken into account. And so the career path itself is universally slower around the world, whether it's US or Ghana or Lithuania or anywhere in the world. Turns out that this kind of a study has been done across the world, and it doesn't matter where you are. This is a universal issue. So when you have something that obvious, let's look at it more carefully and try to fix it. So these are the kinds of issues that are possible to change and go forward. But for me, one of the most inspiring pieces was actually to go back to Google and say, okay, I don't want to see only, what the men have done in physics, because that's actually what's in all of our textbooks as well. Open up a standard physics textbook. You're not going to see the name of any women in there. However, they are there. It's just that we have to look a little bit harder. So I went and looked, and I want to tell you that women do choose physics, and they have been doing physics because we love physics just as much as anybody else out there. And those who don't like it, of course, don't like it, but those who like it, they love it, like me. And like somebody like Vera Rubin, who was the woman who, she really saw invisible stuff. She's the person who actually observed how stars in galaxies rotate. And from the rotation rate, she realized that there's all this, missing matter, meaning missing in the sense that we can't see it, kind of like how Google can't see women physicists. She's the one who found the first evidence for what we now call dark matter. And we still don't know what it is, and we still can't see it with telescopes, but we can see its impact on things like, gravitational effects. So she is this incredible woman who started this whole new area of research, but we see her to be as invisible as the matter that she was studying. And she's not alone. If you look in, for example, in India, Bibha Chaudhary is this amazing woman who for a long time was not well acknowledged because her work was not celebrated. But if you see on the left here, you see these little tracks of dots which look to you and me, maybe they seem like ant tracks, but to her, this was her observations of cosmic rays and the particle tracks left in these photographic plates that she would place high up on mountains to try to detect these invisible particles. She too was looking for invisible things, and she too was invisible. And from studying these kind of tracks and the curvature and the rate at which these tracks were being laid down in terms of the spacing and the curvature, she could calculate together with her mentor, D.M. Bose. They calculated this new kind of particle called a meson that had never been observed before. But they couldn't continue because they didn't have enough equipment. This was during World War II. And so they stopped. And then a few years later, using these exactly the methods that they had developed, this British guy, Cecil Powell, was the one who actually officially discovered this new particle called a pi meson, and he won the Nobel Prize. So this is the level of work we're talking about that women have done that we are, somehow not aware of at the same level as some of the men work by the men. And another one that I want to mention, because it's very closely related to the kind of physics that I focus on, which is quantum physics. This is Cecilia Payne. And she was basically, she was the first woman to do a PhD at the Harvard Observatory. And it was an incredible PhD because she was studying the spectrum of the sun and other stars, where you look at all of the different frequencies and the rainbow colors of light and try to figure out what is the chemical composition of these stars. So all these dark lines, the missing light, is essentially like a barcode where you can actually identify what are the elements in the stars. And by observing that, at the time, all of these different spectra had been studied and cataloged. There were hundreds of thousands of stars that had been cataloged, and they all looked quite different, and they were classified into different categories. It was like zoology of stars. There were so many different types. And she looked at them all, and with this hundreds of thousands of spectra, she applied at the time, in fact, Meghnad Sahad's equations, which were some of the first equations being used to understand these kinds of spectra. And she applied that to these spectra and realized that all these different categories, in fact, they were only different because of temperature. Really, the chemical composition was the same, and all stars are basically made up of hydrogen and helium, mostly hydrogen with a little bit of helium, which today we think of that as a standard thing that everybody knows. But it's not like if I tell you everybody knows that the stars are made up of hydrogen. It's not that we say the stars are made of hydrogen, and that's what Cecilia Payne-Gaposchkin first discovered. We kind of miss out on that final part, and that's a big thing to leave out, because that's a pretty big discovery to understand the entire chemical composition of the universe from something which looked so different when she started. Anyway, that was her PhD thesis, and she eventually went on to become the first head of department of any first woman to be the head of any department at Harvard. So that's Cecilia Payne-Gaposchkin. This is the level of women that we are ignoring in our textbooks. So maybe we should be changing that. To me, this particular story was extra inspiring because of that early use of quantum theory. To me, that spoke, and I was very excited about this field, and so I went on to study more about this in my undergrad years already. I got to do an undergraduate project on quantum theory, and eventually in grad school I focused in on a particular project which I think is close to my heart, because again it was about trying to observe something invisible that nobody had seen before. And that was to try to observe the motion of an individual atom. And we can't just shine a microscope on atoms and see them because they're far too small. So you have to be pretty smart about looking at an atom. And the way to do it is to actually see how they interact with light. So if you shine laser beams at, let's say, a cloud of cold, very cold atoms, then you can control the interaction in such a way that you then look at the light itself after the interaction, and the atoms leave an imprint of that interaction in the light polarization itself. So by measuring the laser polarizations, you can actually get an image and reconstruct actually some of the properties of the atom. So that's what was one of the projects that I was working on when I started as a PhD student. Now I myself I do theoretical physics, but I worked in collaboration with experimental groups who were looking into these areas. And so it turns out it's quite challenging in the lab. For me, it was actually easier because I could do the calculations, but the lab work is, of course, far, far more tricky. But over time, this process was, in fact, cleaned up, and we were able to actually image these invisible atoms. And here's a little reconstruction of what it looks like. So, quantum theory tells us that you can't know for sure exactly every single property of an atom precisely, because there's a principle, for example, uncertainty principle, which tells us it's not possible to know it all perfectly. So the best we can do is try to figure out the probability, the likelihood of, for example, in this case, what is being plotted is the probability of a particular property called, the spin or the angular momentum, which has a particular vector. It lives on the surface of a sphere. So the red shows where it's most likely to be, and the blue is where it's least likely to be. But this is actually data, meaning that this is not just my theoretical calculation. This is reconstructed from the laser properties to try to visualize this particular single atom. Now, of course, the atoms, there's about 1 million in each cloud, but they are not interacting, and they're identical. So you can use all of that data together to figure out exactly the reconstruction of a single atom. And you can do this over time, and you can control how these atoms evolve and basically put the images back to back over time and make a movie. So that's what we did. And here's an image of the evolution of an individual atom, which had never been done at this scale before. So that was really fascinating to be able to see something that is invisible, which is why this is the theme of what I wanted to talk to you about. And it's not just about being able to see it. Of course, this is part of how we eventually study the properties of these atoms and then understand how to control them and make predictions, understand better the laws of physics, and about building technologies such as quantum. So that was, really fun to be able to do this work, and that eventually led me to the field of quantum computing. Now, this is sort of like an area where you have to blend in a bit of computer science with quantum physics. As I mentioned, the laws of quantum physics are a little bit strange because it's all very probabilistic, meaning precision is not really the main aspect of it. In fact, imprecision is really the key to understanding the quantum world. You have to expand how we think about calculations themselves. So a quantum computer is not just another faster, better, regular computer. It's not like the next generation Intel chip or Mac or anything like this. It's fundamentally different because it's a different framework of computing itself. Standard computing is where things are fairly surprisingly simple if you think about it on a very conceptual level. A computer is nothing but a machine that combines zeros and ones. And when the machine itself, of course, doesn't know what is a 0 or a 1, we tell it through things like circuits being switched on and off. So on is 0, off is 1, for example. And all of our calculations, amazingly, can be reduced to this one universal language of combining zeros and ones, which is pretty lucky for us because we don't have to really worry about going into a more complicated space for calculations. This binary logic is universal, which is wonderful, but turns out it's actually quite limiting, which we didn't really realize until recently because it does the job. Of course, our emails and our computers work perfectly well. However, as I mentioned, there are certain types of calculations, such as the quantum chemistry calculations, that are still very, very difficult. It's not like they're impossible to do, because as I said, our current computers are already universal, but they are very, very inefficient to do. So the reason for that turns out because our binary logic itself is not the perhaps most efficient framework for doing calculations. It can be done, but it's not necessarily efficient. And so quantum computing is about broadening that framework and realizing that, wait a minute, why are we stuck with a 0 and a 1? That's two things. That seems kind of a small set to work with. What if we could go beyond 0 and 1? And that's really what quantum computing is about, to say, wait, in the quantum world, we said that there's this uncertainty, meaning there are probabilities. There could be a probability of being a 0, and there can be a probability of being a 1, but you could have some intermediate situation, a state that we call a superposition, some probability of 0 and some probability of 1, we don't know. And that might seem like not a good thing to do in computing, because you want to, in the end, of course, you want to have a precise calculation. So what do you mean that we should be expanding and moving away from precision and going into this probabilistic world? That might sound like a bad idea, but think of it in this other way, where you flip your perspective and say, well, no, we're broadening. We're going from just 2 points on, let's say, that sphere, to which 2 points would be, let's say, the North Pole and the South Pole. But what if we could move our computational space could move through the entire sphere? That would be a much bigger space to work in and would perhaps be more efficient. So that's a conceptual way of trying to rethink and reframe how we even describe computing itself. So that's the basis for quantum computing. And that's why it's not just another faster Intel chip. This is a completely different kind of computer, which takes into account this idea of probabilities. Not only can you do better computing, but there are other kinds of applications that are not part of our current computing framework that could be done using this kind of new approach. So this is where things actually originally started, where before these computers were built, there was this idea of how we can manipulate these probabilities in the right way. So current computers, quantum computers, don't look anything like your laptops or our phones. So here's an image of IBM computer. You may have seen it because it's, of course, these things are making the news all the time these days. So this is 2 pictures. On the left, you see this white cylinder, and that's the quantum computer. And if you open up the cylinder on the right, you see this beautiful chandelier. Now, that's not the actual computer. The processor itself is this tiny little thing right at the bottom, which you can't really see. The rest of it and all of the electronics you see in the room is just to control this processor. So it's not an easy thing. It's kind of like, the old days when, the first computers used to also fill up a room because they were made up of vacuum tubes. And then that changed once, the integrated circuit was developed and so on. So right now, it's almost like the vacuum tube stage of quantum computing, where these computers look really big and they are very hard to control. And one of the biggest challenges is to make them work without them overheating, because heating is a big problem and there are errors when you have these quantum calculations happening. And heat actually destroys these superpositions. The probabilistic description gets destroyed, and that's bad. So most of what's happening in this room is a way to try to preserve the probabilistic world of these quantum processors. And that's very challenging. When I say heating, the cooling required for these processors, you have to be colder than outer space. So it's very, very challenging. And you have to do some kind of error correction, which is another layer to add to this, which is so challenging that it's not actually being done by any of these major companies as yet, but that's where they would have to go. So that's one sort of big barrier to quantum computing. But the payoffs can be really huge. For example, not only can you do computing, but in fact, the whole field started because it was realized that this whole quantum uncertainty idea allows for better encryption, in fact, unhackable encryption. So in the 80s, two scientists figured out that you can encode information in such a way that you use this law of uncertainty. Because things at the quantum level, because you have these quantum bits which are neither 0 nor 1, they are in the superposition. That idea actually leads to another very important result, which says that you can't actually copy this information perfectly. It's called the no cloning theorem. And that's a very good thing if you're trying to prevent a hacker from getting at your data. So that's what was realized in the 80s, that this is actually a way to hide information. So encode the information using quantum uncertainty in such a way that nobody can copy the data. And if they try to read your data, you can actually tell. And so anytime a hacker tries to touch your quantum information, you will know about it, and then you can make sure that that doesn't happen, and resend your data and create new keys and so on. So that's the basis of this unhackable encryption system called quantum key distribution. And this is actually what started driving the field starting in the 80s. And as the technology got better and better to create these kinds of encoded quantum information keys, we are now at a point where we're thinking about things like large-scale satellite-based quantum communication and quantum key distribution. And that's also a big area in many parts of the world. For example, China has launched a satellite to do it, but India also is a major player now in the game, and there's lots of funding and great work being done in this field over here. So quantum communication, a future quantum internet, would be very exciting. Although on the front end, probably most users, excuse me, wouldn't see this happening, because it would be on the back end, the encryption that would change. But that's on the communication piece. On the application side, the quantum computer that I showed you, IBM's machine, it's a prototype. Certainly it has lots of errors, but as I said, even given all the challenges, the payoff could be so big that it's worth it. Governments, companies are spending billions on this. Why? Well, I already told you a little bit about the communication security potential. The only known completely unhackable encryption protocol is a quantum protocol. Healthcare, I also talked about, and imagine being able to really, make more efficient ways of simulating these quantum molecules, and really understanding the whole landscape of different quantum materials for all kinds of applications. Environment also I talked about a little bit. Another big problem that I think we've learned over the last 2 years is this idea of logistics and supply chain, our transportation routes, connecting the world in some way is a very hard problem. It's actually an optimization problem. And turns out that one of the areas where a quantum computer might be good for using is for optimization kinds of questions. Now, a quantum computer is not universally better than a regular computer from what we know. There are many calculations where quantum does not offer any extra speed up that we know of. So we want to focus in on the algorithms that we already realize can be better. And those include some of these kinds of applications. And certainly one thing that a lot of private companies, of course, are interested in is in trying to look through and sort through big data sets, such as financial data sets, and try to do some kind of quantum search, or even use security to improve on things like blockchain and so on. So these are all of the potential applications. So even though right now, the effort required to scale up these quantum computers is huge, it's not currently efficient or in energy sustainable at all. However, just the potential of where we could go is what is driving the field. And there's a huge number of both governments and companies in the field. So I'll give you a little bit of a sort of summary of all the hardware companies. There are some big names, IBM, Google, Microsoft, everybody's in the game. But there are also new companies like D-Wave and IonQ. IonQ actually became the first quantum computing company to be publicly traded. So it sold, it's part of the New York Stock Exchange, and you can buy shares now in that company. So that's how much this whole field is being driven into the real commercialized industry. There are many software companies, because of course you need to program these kinds of quantum computers. And programming something for building superpositions and uncertainties is a little bit different. So you can't, I mean, there are now front ends where you can just use regular codes like Python, and the back end, is used to translate that into running a quantum computer. But it still takes a new kind of language. And some of this you can try out because a lot of these companies want you to learn this stuff. So they are offering, free access to some of these options. So if you go on Microsoft, IBM, Google, you can play around with some of this. So it's kind of a fun time to look into this field. But to go back to what we were talking about in the beginning about, what does this field look like? What does the physics community look like? Who is part of this new quantum revolution? Well, for fun, I went into IonQ's website because they were in the news, because they just, started, selling their stocks and so on. And this is what I found for their leadership, unfortunately. So as you can see, it's very homogeneous, and I guess they forgot that there's a whole group of people and potential talent out there that they are not including at all in their plans for the future of quantum. So it looks like we're making the same kind of mistakes as before and not really including all of the potential workforce, especially in quantum, where we will need this. If there's really going to be this huge expansion in the industry, then it's not very wise to be building companies that only involve, for example, men in this case. So I hope that the future is better. I don't want to end by, this kind of bad news message. So I'm going to show you another image that's one of my favorite photos, because this was a photo taken at a conference held in Canada, the International Conference on Women in Physics. And everybody in this photo, all these women are physicists from all around the world. We had more than 50 countries represented. So women are doing physics all over the world. Women are now leaders in every area of physics. You pick one and there's leading women physicists in the field. So certainly the field is growing and expanding, and it's for the better, because I think, certainly in my area, we need a much larger group of researchers coming in and growing this field. And I think it's better for everybody, including, those who are already in the field, to have all these new ideas, and who knows what kind of physics we'll do in the future. So the quantum revolution is exciting, but this revolution is really the one that I want to see in the future. So thank you for listening, and I'm happy to answer questions about quantum as well as my own career, if you have any.
Thank you, Shoini, for an excellent talk and bringing actually both the aspects of this series of talk together. And the movement was so smooth that for some time we didn't realize that you moved from one part of the topic to the other part. And so it's now open for questions, comment, discussion, anything means, and especially from the young students.
Also on the chat, I think you can write your question.
Yes, you can write in the chat, or you can also unmute yourself and speak.
Professor Ghosh, I have a small question. You told that the temperature you have to maintain, the IBM thing which you have shown there.
Yeah.
The temperature you have to maintain, it is very lower. So what is the range of that temperature now which you have to maintain to create that quantum computer, you can say?
We're talking millikelvin, I think, is what they are. I don't know the exact details, but we're talking, I'm pretty sure it's in the millikelvin range, because their computer is based on superconducting qubits. So those have to be, really, really cold to maintain coherence. Yeah.
Okay.
I can see a question in the chat room.
Yes, let me read it. Can you please throw some light on applications of QC on healthcare domain? So there are several different areas. So there's quantum computing, and then there's also quantum technologies, which may not be a computer, but they are quantum based. So for example, there's a lot of work on quantum imaging and quantum sensing. So that's all that there, the healthcare application is is clear because, of course, you know, when you go to the hospital, of course, you know, there are many types of different imaging technologies already existing. And some of those can be improved if you use, you know, entanglement-based imaging, for example, and quantum sensors are something that are being developed a lot. So that's one area. For the computing side, as I was mentioning, the key area that people are focusing on is trying to show, right now it's just a testing benchmarking thing. We're trying to show how you can build quantum algorithms to calculate things like the structure of different molecules. When I say structure, I mean what are the energy levels and so on for the, you know, the atoms in a molecule. Now, right now, for example, there's been, if you look online, you can see there's been some sort of proof of principle calculations where take something that we know very well, let's say a water molecule, and see if the quantum computer can calculate it and how much faster can it do it compared to a regular computer. And those kinds of benchmarks are being done because at some point you can then use those same algorithms to calculate molecules that we've never been able to calculate before. And those will help us to develop understanding of, you know, the properties, you know, the chemical properties of something that may be useful to treat, I don't know, Alzheimer's maybe, or some other, you know, of the many diseases that we have to be thinking about treating. So this is what this area is called, quantum simulations. And the near-term goal would be to try to do this kind of work. And you don't actually need a very, very large computer to be able to do that, because even a finite size molecule, what you could do is try to get close to the answer that you're looking for, and then use that to just redo calculations in an optimal way on a regular supercomputer as well. So a hybrid approach would perhaps do the job in the near term before perhaps in, you know, longer term when really large scale quantum computers may be built. We don't know yet. We don't know if that's even possible, because maybe it'll never be possible to scale up to a very large computer. But in the short term, maybe something that's a hybrid may still work. So those are some of the areas people are working in.
So any other question, comment? So this is a comment only from Sandeep Marsing on the chat.
Thank you very much. And I hope that more, if you are considering a career and you don't know where you want to go, then more of you will now consider following not just physics, but any area that you feel like you're interested in it, but you're not sure if you fit in. Well, I hope you still try to explore it.
Any other comment, query, question?
I could come in at this point. Thanks, Professor Ghosh. It was a very, very interesting talk, and always a pleasure when we see that, you know, women in physics are now also talking about the need for exponential increase and going beyond. So at institutional level, changes are required, you know, to improve the gender climate and culture. Has something of that kind been undertaken in Canada to have a more structured change in policies to have more women come in? And especially, as you said, you know, in areas such as the rarefied areas of physics, like you have today spoken about. So I believe Canada is part also of, you have launched Dimensions.
Yes, yes.
And I'd like to know a bit more about it, because I'm leading a similar initiative in India. We call it GATI, Gender Advancement for Transforming Institutions, where we have 30 pilot institutions now trying to, you know, bring about, as the name suggests, transformative change over a period of time. So I'd really like to know about Dimensions.
Wonderful. So yes, Canada has recently, in 2019 was when it all really started getting rolled out, but it actually takes more than a couple of years for, you know, this large national initiatives. So
Yes.
Dimensions is really a program that is based on another program from the UK called Athena Swan,
Right.
which has existed for much longer. And the idea for Athena was that, a group of scientists actually came up with it, saying, well, different departments, and so it started in physics and then it grew. The idea was that different departments would do self-assessments to try to understand of course, the numbers as in proportion of men versus women, students, faculty, staff, and so on. But also, what are the experiences of everybody in the department? What are the different resources, as I was talking about, the funding, the things like support for childcare and things like that. So just a full scale assessment, an environmental survey, really. And then based on that, in the UK, what happened was they started getting ranked. And there was not even any actual award, except, there was gold, silver, bronze kind of ratings. But it became this competitive thing. And so all these different departments started jumping in, and everybody wanted that, gold standard and so on. And that automatically started people thinking about this and working on these kinds of issues. So it raised awareness more than anything, to be honest, but there was no real funding or financial support for this. So in Canada, what happened was the same kind of idea was started, where institutions had to sign on to do this kind of assessment work, but the government is funding it. So I think that's an important piece, where you want real sort of support in terms of time and effort required. It's quite significant, and often it falls on the women in the institution, or somebody who's seen as the person to do that work, and that's an extra piece, extra work, and there's no benefit necessarily for them, and they lose out on their research work. So Canada is trying to put some money behind this and roll it out in a way where there's actually capacity to do it. And then the idea is similar, where each institution, not just a department, each institution now will be assessing where they stand, and then they have to have a roadmap for improvement, and then be able to show that they are reaching these goals. So it's a very structured process, but we're just starting. So I hope I can tell you more once we have that kind of data.
So we are doing something similar, because it's inspired again from Athena Swan. And so I'd like to continue this conversation with you as we go along.
Wonderful.
And see, the commonalities and how things can be. Ultimately, it has to be scaled up. We are doing it at a pilot level with 30 institutions. So more than anything else, it changes the vocabulary, and it brings the problems center stage.
Definitely.
Anirban, can I ask a small question?
Yes,
It's
sure.
not actually a question. Many young students, both men and women, talk to me that they want to do physics. They are interested to do physics, and say they are in the BSc level, bachelor's degree. They want to do master's and PhD. But what are the job opportunities after PhD or after postdoctoral fellowship and things like that? And in India, things are not that bright right now, although it should be very bright, because there has to be a much, much greater investment in science and technology. But the job opportunities for young men and women are little limited, in my opinion. 50 years back, things were not, when we came back, the salaries were very low, but the jobs were there. But not anymore now. So what I want to ask you is that what is the perception in a country like Canada, which we can emulate or something like that, that a young, bright student, does he or she wants to do physics or mathematics or something like that, or they are also concerned about the job perspective for such a bright young student there?
This is the same universal problem that I think students today certainly have a lot of anxiety about future careers. And the truth is, certainly in physics, the perception is if you really study physics and go all the way through to PhD, then the natural steps would have to be an academic career. And there's certainly very, very limited options, especially in Canada. We have only a very finite number of universities. And there's no private universities in Canada, right? So there are only the government funded ones, and that's it. So it's very much set in stone, and there's no expansion. So academia itself is certainly not going to work out for the majority of students who want to do physics in Canada, certainly. However, the numbers show that actually if you do a degree of undergrad or even higher in physics, your employment rates are higher than the average. So a physics degree and a mathematics degree certainly makes you employable. It doesn't mean that it will be in an academic career, and it certainly doesn't mean that it will be exactly in the, let's say, your PhD area. But the beauty about physics and mathematics degrees are they provide you with those skill sets. So a lot of our students will go work in industry, for example, in certainly in telecoms or in the computing sector. So IT in general, as we all know, is exploding everywhere, and it's not going to stop anytime soon. So I think that it needs a sort of a shift in how the students present themselves as employable in these areas.
So getting the employability is also a problem in Canada. That's what you're trying to say.
In the academic sector, yes. But
Yes,
more
yes.
broadly speaking, actually, as I said, certainly the graduates from, let's say, our undergraduate physics program we are quite proud to know that actually they have 100% employment rate from what we've been able to track. So that's the good news story there. Why? Because of course they have these great skill sets. So they can go work in banks, they can go work in computer science industry, they can work with the optics industries, telecoms. So they do actually have a broad range of potential careers, and they do take it. They can adapt easily. That's what's, I think, really great about a physics degree, and math, of course, in general. So, yeah.
Thank you so much.
Any other question? Especially, I'm looking for questions from students. Any query?
Don't be shy. Ask that one thing that you've always wanted to know. Now's your chance.
Hello, Sohinidhi.
Hello.
Wonderful deliberation. Huh? Nice to hear you once again. Actually, you came HRI in 2015. I am
Yeah.
Thank you so much. Wonderful deliberation.
Thank you.
Any comment, questions from anyone else?
I think we can go for a photograph. I request all the participants, please.
If you are comfortable, please.
Please switch on your camera so that we can take a photograph.
Anurag, after this is over, I want to talk to you.
Yeah, I have done it. Yeah, thank you. I have done it.
Chalo.
Still, before we close, means if anyone else has any query, comment, anything to say. Swarnali, are you saying something? You're muted. So if not, we thank the speaker once again, and we just before we close, we note that the series will continue, and this was part of 75 years of India's independence, and as NASI is always interested to connect science with the society, and this particular series is part of National Academy of Sciences India's Science and Society Initiative, and as you probably all know that this academy was founded by Professor Meghnad Shah, and in part of the talk, Professor Ghosh mentioned about Shah's equation, and that was a exciting connection somewhere in the middle, that the founder's name appeared spontaneously in the discussion. So it was wonderful to have Professor Ghosh with us and giving an exciting talk, and to have all of you as in audience and some more students in the YouTube. And we'll continue with this series of lecture. And next lecture, we'll announce the date soon. Will be on fiber optics, and the speaker will be Professor Enakshi Sharma. And with this, I'll thank you all and close this meeting. So thanks, Sohini, once again. And my students will continue the technical discussion separately.
Yes, thank you. I look forward to that.
Thank you.
Thank you for organizing this, Anirban and Papia. Thank you very much. And all your colleagues.
Thank you.
And thank you, Sohini.
Thank you, everyone. Thank you, Professor
Thank
Ghosh.
you all.
We were on online.